Welcome. Today, we're going to pull back the curtain on the hidden logic that pretty much runs our digital lives. We are talking about classification, these incredibly powerful algorithms that sort, organize, and make sense of the absolute flood of data that's all around us.
You ever stop and think about that? How your email just knows which messages are junk and which ones you actually need to see? I mean, it feels like magic, but it's really just some brilliant data science at work.
And it's not just your inbox. Think about when you search for something online. How on earth does that search engine wade through billions of web pages to decide, yep, these are the ones you're looking for?
Well, the common thread connecting all of this is a really powerful data mining process called classification. It's the engine that takes this messy, chaotic jumble of information and neatly assigns everything to a predefined category.
Okay, so here's our game plan. We're going to start with the big question. What is classification? Then, we'll look at decision trees as guides. After that, we'll see how probability helps us detect threats. Then we'll see how we can go from trees to simple rules. And finally, we'll wrap it all up with how this enables data-driven decisions. All right, let's start at the beginning. What exactly is classification when we get right down to it? Okay, so at its core, classification is what we call supervised learning. The best way to think about it is like you're teaching a toddler with flashcards. You supervise the computer by showing it tons of examples that are already labeled correctly. Like here's a huge pile of emails already marked as spam, and here's a pile marked not spam. The algorithm studies these to figure out the patterns so that later it can take a brand new email it's never seen before and put it in the right category all by itself.
So our first approach really puts this idea into practice. Let's say you're a search engine, and your job is to figure out which web pages are the most important ones. How do you automate that? Well, one of the best ways is to build a decision tree. And the CART algorithm is a fantastic tool for this. Honestly, just picture a giant flowchart for making decisions. At every single step, it asks a simple question about a web page's features, like how many links does it have, or how often does a certain keyword show up. And it uses these questions to split the data into cleaner and cleaner groups. So how does it actually build this flowchart? Well, it's pretty clever. It starts with all your data in one big pile at the top. Then it searches for the single best question to ask, the one attribute that splits that data most effectively. It creates new branches based on the answers, and then it just repeats the whole process on each new, smaller pile, getting more and more specific until it finally hits a clear answer at the very bottom. And if you were to actually do this with a programming language like R, it follows a really logical path. First, you load up all your data about the web pages. Then, you tell R to build the CART model, which learns all the patterns for you. After that, you can start feeding it new pages to see what it predicts. And finally, and this part is absolutely crucial, you check its work. You have to evaluate how well it did. Is it actually any good at finding those important resources? Okay, let's switch gears to a place where the stakes are a lot higher, cybersecurity. Now, we're not just organizing web pages, we're trying to spot dangerous things like malicious network traffic or spam. Decision trees can work here, sure, but for this kind of thing, there's another approach that's often even better, using probability. And that brings us to our second method, Bayes classification. At its heart, it's a statistical algorithm. So instead of a flowchart of yes or no questions, it thinks in terms of probabilities and likelihoods. It's a whole different way of looking at the problem.
The real magic here is how it balances two key things. On one hand, you've got what's called the prior probability. That's basically asking, what do we already know? Like, what percentage of all emails in the world are spam? But then it combines that with the likelihood. That asks, okay, given this new piece of evidence, say an email contains the word Viagra, what's the probability we'd see that word if the email is spam versus if it's not? It's this beautiful blend of old knowledge and new evidence. Now, in the real world, trying to calculate all those interconnected probabilities would be, well, a nightmare. That's why for jobs like text classification, we often use a faster, simpler version called the naive Bayes classifier. It makes a naive little assumption. It basically pretends every word is totally independent of all the others. Now, we know that's not really true, but this shortcut works surprisingly well for things like spotting spam. Okay, for our last method, let's jump into a completely different world, video games. How could you automatically figure out what kind of player someone is based on how they play? Are they an explorer, an achiever, a socializer? This is where we can move from complex trees to simple rules.
And this leads to one of the coolest ideas in classification. Seriously. You can take a big, complicated decision tree, and for every single path from the very top to a final answer at the bottom, you can turn that path into a simple, easy-to-read if-then rule. Something like, if a player explores more than 90% of the map, and they complete less than 20% of the quests, then classify them as an explorer. So simple, right?
So this creates a really important difference in how these systems work. With a decision tree, you're locked into following one rigid path to get one single answer. But with a rule-based system, you've got this flexible collection of independent rules. A player's actions might actually trigger several rules at once, which can give you a much more nuanced picture of how they play. So how do you even generate these rules in the first place? Well, a really popular way is called the sequential covering algorithm. It's actually very intuitive. It finds the single best rule it can that covers a good chunk of your data. Then it just takes all the data that rule explained and sets it aside. Then it repeats the whole process, looking for the next best rule in what's left over. It's like it's learning one piece of the puzzle at a time.
Okay, we have looked at trees, we've looked at probabilities, and we've looked at rules. Let's zoom out for a second and take a look at the bigger picture here.
So here's a really quick summary. Decision trees, like CART, are absolutely fantastic when you want a visual model that's easy to explain to someone. Naive Bayes is a rock star for text classification. It handles things like spam filtering with this amazing probabilistic skill. And rule-based systems, they're perfect when what you really need is a set of simple, readable, if-then statements that anyone can look at and understand.
At the end of the day, everything we've talked about today goes way beyond just some lines of code or abstract theory. These algorithms are so much more than that. They are powerful, practical frameworks that let us make sense of an incredibly complex digital world. These are the tools we use to find the signal in all the noise, to bring some order to the chaos, and to turn mountains of raw data into decisions we can actually act on. And that leaves us with a really fascinating thought to end on. From medicine and finance to marketing and gaming, these methods are popping up everywhere. So the real question isn't what they can do, but as our world gets even more full of data, what will we ask them to classify next?